Okay. Hey, everybody. I am Alex Young. I'm the Associate Director for Science in the Heliophysics Science Division. And what I'm going to talk to you about today is actually, Randy gave a great discussion about a lot of the technology, a lot of the challenges. I'm going to talk about some of the aspects of the environment that we have to deal with out in space, and the culprit, the main culprit behind all of that, the troublemaker, the sun. The sun, which is the driver of everything in our solar system, and creates this complicated environment that fills the whole solar system. It creates, in fact, this structure around the solar system we call the heliosphere, and interconnects all of the things in the solar system: planets, moons, asteroids, comets. Even the technology that we put in space to study all of this is impacted by this environment created by the sun. So before I go any further, who here was able to observe the total solar eclipse at all? Okay. Who here saw totality? Fantastic. That's fantastic. So when you were looking at the corona, this is the outer atmosphere of the sun, and this is the atmosphere that is driven by and controlled by magnetic fields coming off the sun. And in fact, that atmosphere extends out into space, and it is what creates this bubble we call the heliosphere. So in fact, we are all living in this extended atmosphere, which is streaming away from the sun. This soup of particles and fields that's creating this really complicated, exciting environment. So, actually, I'm giving the controller. Here we go. This is the. Is it not on? Oh, can you just advance it? Just go ahead and advance it. All right. Okay. So the next image I'm going to show you is the sun, kind of like what you think about it from the ground. Now, I'm cheating a little bit because this is a really high-resolution image taken from space, but this is the visible sun. The sun, the photosphere, the layer of the sun that we observe in visible light. If you had your safe solar viewing glasses on and you walked outside and put them on to block out some of the intense brightness, this is what you would be seeing, the disk of the sun. In fact, if there were sunspots, that's what these dark objects are, were on the sun right now of this size, you would see them from the ground. These are larger than the Earth, okay? And this is, in fact, where the magnetic field is coming from. And you see all this activity, all these little shimmering bubbles. These are, in fact, little bubbles of solar material that's floating up like bubbles in hot water, okay? Convection cells. These are about the size of Texas, okay? They're huge. To give you just to some scale, I could fit 110 Earths from one end to the other, okay, to cover this. But if we step out into space and look at the sun in other wavelengths of light that don't make it through the atmosphere, fortunately for us, things like X-rays and ultraviolet light are hazardous to us, but because the atmosphere is protecting us, we don't have to worry about it, except we can't see it. So we have to go out into space. And if we do that, we see a totally different sun. This is one wavelength that we can observe the sun in, one of many, extreme ultraviolet. And look how much more complicated it is. You can see stuff happening all over it. And in fact, you see that bright flash and then that huge blob of stuff coming out. That's sitting over one of these sunspots that erupted. It became unstable. That flash of light is what's called a solar flare. Enough energy released in that flash to power the world for 100,000 years. And that blob of stuff that's flying out, a lot of it you see fall back on the sun, but in fact, just as much of it flew out into space at millions of kilometers an hour. And that has enough energy equivalent to what we saw from that solar flare. To again give you some perspective, here's a quarter in my hand. This is about the size of the Earth. This is really big. And so that thing flying out into space, so you can see that because we're looking at it in other wavelengths, we can now see a unique perspective. With the Solar Dynamics Observatory, we in fact can see 10 different wavelengths of light, starting from ultraviolet into slices of extreme ultraviolet, and then we still see this visible light that we're familiar with. But look how much different the sun is. Now, the colors are simply labels we put on there. The colors, the images are actually black and white. We put colors so we can distinguish between the different wavelengths. But what you're seeing is different temperatures of the sun, starting at about 20,000 degrees, 80,000 degrees, 100,000 degrees, up to a couple million degrees. So we're seeing that the atmosphere, we're actually also looking at different layers. As we go up in temperature, it gets hotter. And that's totally bizarre. When you walk away from a campfire, you don't get warmer, you get colder. But when you move away from the sun, it actually gets hotter as you're going up. And so this part you see here is the very beginning of the corona, what you saw during the total solar eclipse. And now we can see all that in incredible detail. Now, we looked at the eclipse from the ground because, in fact, we can't see the eclipse in visible light except during a total solar eclipse. So that's the one thing that even the most advanced spacecraft can't do. So nature gives us an opportunity to see this unique view of the atmosphere of the sun. And here you are seeing a comet flying towards the sun, and watch for a second, you'll see this wave comes past it, and you see the tail disappear. You see the tail break off from it? The stuff flowing out of the sun is actually interacting with that comet, and it's pulling the back of the comet's tail off. What you're seeing is this constant stream of material that's flowing out of the sun, we call the solar wind. It's like this ongoing low rain that's happening, or the background waves are happening. And then every so often, you'll see one of those large explosions like you saw earlier, riding on top of that. This big blob of stuff, billions of tons of solar material traveling at millions of kilometers an hour with huge magnetic fields in it. And what it does is that when it interacts with planets, other bodies in the solar system, it creates this soup of particles and fields, things we can't see. If your eyes could see energetic particles, if you could see electromagnetic fields, this is what your eyes would see when you looked outside the Earth. You see all of these particles are streaming around. In fact, they're following the magnetic fields of the sun because these particles are electromagnetic and they interact with it. And this is creating this amazingly complicated but also hazardous environment that we're seeing in different forms all over the solar system. So when we plan to travel beyond our local area onto other planets, we have to think about all this stuff we're traveling through. There's radiation, there are all kinds of particles that can interact with our technology. We've seen this stuff happen on the ground. We've actually seen these huge explosions reach the Earth and mess with our power grid, with our communication satellites. One of my colleagues is going to talk more about this whole area called space weather. But this is this crazy environment that the sun is creating when all of this stuff is being shed from it. And if we were to look at what would happen, when we look at all of this, we need a huge suite of spacecraft in order to observe it. We want to look at the sun, we want to look at the other planets, we want to look at what's happening down on Earth. So in fact, we have a whole fleet of spacecraft orbiting close to the Earth, orbiting around the Earth, in fact, orbiting through the whole magnetic system of the Earth itself, because the Earth is actually a giant magnet, and it interacts, as you saw, with all of this stuff. So we call this the Heliophysics Fleet, and this gives us a giant observatory to really study this heliosphere from the sun all the way out to the edge of the solar system. In fact, one of our spacecraft, which is a planetary heliophysics mission called Voyager, has now gotten to the very edge of it, and in fact passed through what we think is the heliosphere into interstellar space. Our first touch of other objects. And now, as Jim Green has talked about, we even have an object that's entered our solar system that's an asteroid from outside the solar system. So we're starting to connect beyond our own solar system and measure and see things like we've never done before. So back in 2012, in July, we had an explosion like this, and it actually went off to the side of the sun. I'm going to skip ahead and show you. Oh, I think I missed it. Can you go back? It's the Carrington Event. So this event happened off the side of the sun, but what we did is said, well, what would happen if this event actually was directed towards the Earth? So we took our models that tell us about what's happening, and this is a model of the Earth's magnetic field. You see, the Earth's magnetic field is very complicated. The sun is over here, and all that stuff coming off the sun is dragging that magnetic field, making this giant teardrop structure we call the magnetosphere. But you see that big blast come in and hit it, and watch how these magnetic fields that are out here are all of a sudden pushed down almost to the surface of the Earth. So spacecraft or even astronauts that are out here who are in the protection of the magnetic field and the atmosphere, all of a sudden when that giant explosion hits the Earth, it pushes it in. And it also creates all of this energy in the tail, and that energy flows into the North and South Pole, and we get the aurora borealis. So that's the first sign that we have that we can visibly see of the space weather, of this interaction here with the sun and the Earth. All of those particles and material travel down the magnetic fields, and they interact with the upper atmosphere. They interact with oxygen and nitrogen, and they create greens, reds, and blues, depending on which elements they're interacting with and how far up in the atmosphere they are. But we see this all through the solar system. We see aurora on other planets. We see aurora around Jupiter, Saturn, the gas giants. We even see aurora around Mars. Mars doesn't actually have a magnetic field, but it has an atmosphere. And in fact, because it doesn't have a magnetic field, the particles are not following the poles, they're covering the whole planet. So we see aurora on Mars all over the entire planet. So the whole planet is covered with aurora, not just concentrated at the north and south poles. But understanding all of this is telling us huge amounts of information about how life forms on this planet, how life formed on other planets. So understanding what happened on Mars is really critical. Can you play the Mars one, the Maven shot? So looking at the interaction of the solar wind and solar material hitting the Martian atmosphere, which remember, Mars doesn't have a magnetic field. And what we've learned about that is having a magnetic field helps to keep the atmosphere intact over a long period of time. So the fact that billions of years ago, Mars's magnetic field turned off, just all of a sudden, it was slowly eroded away by all of these particles slamming into it. And using the Maven spacecraft, we're able to actually measure and see the vast amount of atmosphere of oxygen streaming off into space. So this is why it's no longer the moist, warmer world that we think it once was. So understanding this process, not just on Earth, and not even just on Mars, tells us about how life could have formed on a planet, how easily or difficult it is for life to form, and ultimately, this is critical for us to understand exoplanets. When we look at other stars and other solar systems, it's not just important to know that they're close enough to their star to have liquid water. We have to know what the space weather environment's like. How much energy is coming off of that star, and how is that interacting with the atmosphere of those planets? And in fact, we think that how atmospheres are formed are driven by the space weather. And it could even be driving the formation and evolution, the spark of life itself. So understanding heliophysics is really the fundamental physics for how a star and all of the bodies in its solar system interact together to create the environment that we live in. And it tells us about the possibility and the formation of life in the rest of the universe. So thank you very much.